In this video, we are going to be focusing on just very introduction acid-base reactions. We will be spending a lot more time with this later in the course when we do equilibrium, titrations, and lots of other work with acids and bases. But in this chapter, we're just going to be focusing on the Bronsted-Lowry definition, which we covered in the first semester of chemistry. And so that you should already know that acid is a proton donor, and bases will accept protons, and that the net ionic equation for a strong acid and a strong base should look something like this, with the hydrogen ion, also could be written as the hydronium ion, reacting with hydroxide to form water.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
All right. Going to the next slide. There are a few steps to perform these calculations. I'm not going to read them one by one to you, but we are going to do a practice problem shortly that will use these same steps. So these are in your notes, and you'll want to refer to those when we do the problem. Acid-base titrations we also did in the first semester of chemistry. You should know that titration is used to solve for an unknown concentration of an acid or a base. The equivalence point is when you have exactly reacted the acid with the base, and the end point is when your indicator changes color. The indicator we used in our titration in your first semester of chemistry was bromothymol blue. We use that because it changes pH at around 7, and because we used a strong acid with a strong base in our titration, the pH of our reaction should end up being at a pH of 7. Ideally, your equivalence point and your end point should be occurring at the same time. If that does not occur, you have chosen the wrong indicator. Here is the practice problem we are going to try. For the titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric to reach the end point? And the end point, again, is when the acid has reacted exactly with the base. Step 1 in the steps that we discussed a couple slides earlier were list the species present in the combined solution before any reaction occurs. So I'm going to write that up here. This is going to be sulfuric acid reacting with sodium hydroxide. Both of these things are aqueous solutions, so really ions floating around in solution. This is before the reaction has occurred. We know that when an acid reacts with a base, we will produce water, which will be in the liquid state, and a salt, which in this case is sodium, Na2SO4, sodium sulfate, which, remembering back to your precipitation reactions and your NAG-SAG solubility rules, this is an aqueous solution. The next step would be to look at these species, what's actually going to exist in solution. And so in this case, it's going to be 2 hydrogen ions plus a sulfate, 2- plus a sodium ion plus a hydroxide. And right here I'm going to stop because I forgot a step, and hopefully you caught that step. And that step was I did not balance the reaction. You have to make sure you have a balanced reaction. So I'll be producing 2 waters and 2 sodium ions and 2 sulfate ions. And I need to make sure that this side also got balanced. And I made a mistake. There we go. So we cross off our spectator ions, and we cross off the sodiums, And so our net ionic equation is 2H plus 2OH minus, producing 2 water. You might notice that all of those coefficients could be reduced to 1. So I have finished steps 1 and steps 2 in that process of solving for acid-base reactions. And step 3 says calculate the mole of reactants. In my problem it said I have 1 liter of 0.5 sulfuric acid. So I have 0.5 molar sulfuric acid, and I have 1 liter of it. That means I have 0.5 moles of sulfuric acid. How many moles of hydrogen ions do I have then? Well, looking at my sulfuric acid formula, for every 1 mole of H2SO4, I have 2 moles of H+. So my moles of H2SO4 will cancel, and you'll get that you have 1 mole of H+. Again, question, how many moles of sodium hydroxide would be required to react with this? So I'm just going to do a stoichiometry problem now. I have moles of hydrogen. I want to find moles of hydroxide. And so I can just continue on here and say for every 1 mole of hydrogen, I would react with 1 mole of hydroxide. You could also put 2 and 2 in here. Obviously the ratio is still a 1-to-1 ratio. Your moles of hydrogen cancel. Just a thought, you probably might be able to figure this in your head, but you do want to consider how many hydroxides the base does have. So 1 mole of hydroxide would be in 1 mole of sodium hydroxide. The reason I say that is because there could be situations where you have a base, something like magnesium hydroxide, in which case the moles of your base are not equal to the moles of the hydroxide ion. And so I calculate, and this calculation is very simple obviously, and it's 1 mole of hydroxide ions, or 1 mole of NaOH. That is the end of acid-base reactions.